Section 20, related rates. This is a section that gives a lot of people problems because it's applications of what is essentially implicit differentiation. Because we have multiple things, variables that are dependent upon generally time. And so we have to take the derivative with respect to time of all of them, and all of them have, just like an implicit differentiation, when we take the derivative of something like x squared plus y squared equals 4. If we take the derivative of x squared with respect to x, we just get 2x. When we take the derivative of y squared, though, because y is a function of x, we get 2y dy dx. It's this term we're going to get a lot of in these sort of problems, because a lot of our variables are changing with respect to time. And so we're going to get a lot of dx dt's, dy dt's, those sort of things. This would be equal to 0, but that's neither here nor there. Okay, a lot of the time the Pythagorean theorem is going to be the useful equation. Trig functions are also commonly used in related rates problems. But let's just jump in and start looking at a few problems. So I'm going to skip the first example problem to go down to some easier ones that I found. Alright, the first one is air is being pumped into a spherical balloon at a rate of 20 inches cubed per minute. How fast is the radius of the balloon increasing when the radius is 6 inches? Okay, so first thing we got to do is know the volume of a sphere, which is 4/3 pi r cubed. We know that the rate that the volume is changing is 20 inches cubed per minute. I know it's volume because it's inches cubed per minute. That is exactly dV dt. This is a volume measurement. That's a time measurement. So dV dt would be exactly that. So I should solve for dV dt so I can plug in 20. So I get dV dt is equal to, I got to take the derivative of this with respect to time. Pull down the 3, cancels out with that 3. I get 4 pi r squared dr dt. So this is evidence of multiple variables being taken the derivative of with respect to time. Alright, so I can plug in things. I get that 20 is equal to 4 pi, okay, r squared. No, we actually know r. R is 6 in this problem. They told us that in this part. So 6 squared dr dt. And what does it want us to find? It wants us to find how fast the radius of the balloon is increasing. Well, that is dr dt. Exactly. The radius, the radius dt. So sweet. We just need to solve this equation. 6 squared is 36 times 4 is 144 pi times dr dt equals 20. And then I can just divide both sides by 144 pi, and I get 20 over 144 pi equals dr dt. And I could simplify this further. 10 70-seconds, 5/36, so 5 over 36 pi is probably as simplified as we could get it. But not only do I need to write it like that, I need to write it in terms of the units. So I need to write that it's inches per minute. So my actual answer would be 5 over 36 pi inches per minute. Alright, next problem. A man that is 5 feet tall walks at the rate 4 feet per second directly away from a street light, which is 20 feet above the street. Alright, 20 feet up. Here's a straight light. The dude is 5 feet away, or we don't know how far the dude is away, but he's 5 feet tall. So he's walking at 4 feet per second away from the lights, like this. So this is what our picture looks like. We have the light shining, we have his head, and his shadow is coming out from where his head, or his whole body here, blocks off the light. And so the shadow is coming down to here-ish. So, okay, at what rate is the length of a shadow increasing? We need to figure out the rate that this distance is increasing relative to his speed walking this direction. So this is a similar triangles problem, essentially. So this triangle here, which is 15 tall because the difference in heights between the light pole and our man here is 15. We don't know how far this distance is, but we do know that this distance is changing at 4 feet per second. So if we called that distance x, then we could say dx dt is equal to 4 feet per second. We know the height of this triangle is 5, and so we can figure out the rate at which this one's changing based off of similar triangles sort of thing. Alright, the trick to this problem is that you don't want to actually set up something and take the derivative. You want to set up a proportion. So 15 over the rate at which the person is moving, which is 4 feet per second, is equal to the height of the person over the rate his shadow is moving, which is x feet per second. And we just cross multiply. 15x is equal to 20. We divide by 15, and x is equal to 1 1/3 feet per second. And that's the rate at which he's moving, or at which the shadow's moving. Is that length increasing or decreasing? Well, this is one where we can kind of just use logic. If the guy's moving farther and farther away, his shadow is getting longer and longer, and so the rate at which it's moving is getting bigger and bigger. So the length is increasing. So sometimes it's easier not to use calculus on it. We didn't use it at all there. Alright, another example. Oil spilled from a ruptured tanker spreads out in a circle whose area increases at a constant rate of 6 miles squared per hour. How fast is the radius of the spill increasing when the area is 9 miles squared? Well, if the area is 9 miles squared, pi r squared is equal to 9. So we can figure out what the radius is at that point. It's 9 over pi is equal to r squared, and r is equal to the square root of 9 over pi. Alright, let's look at the other information. So we want how fast the radius of the spill is increasing, so we want dr dt. We're given the area is increasing at a constant rate of 6 miles per hour, so we have dA dt. So we need to solve for dA dt, so we should take an area formula and take the derivative. So area is just pi r squared. This is a circle. So dA dt would be equal to 2 pi r dr dt. And then we know a lot of this information. We know that 6 is dA dt. We know that r is the square root of 9 over pi. And dr dt is what we're solving for. So now I can divide both sides by 2, and I get 3 is equal to pi times root 9 over pi dr dt. And then I can just divide by both of these things. So 3 over pi times 9 over pi equals dr dt. And that's the rate at which the spill is increasing. And that is in miles per hour. Alright, last not least, we're going to do a cone problem. So this is one takes a little bit more thought. So our cone is going up like this. So we need to find a way to, it's also going up on this side, this is the cone. We need to find a way to relate our height and our radius because they're directly related. When we're this high, our radius is smaller. When we're all the way up, our radius is at its maximum. So the radius at the top is 4 according to the problem, and the height is 10. And so from this, I can figure out that the radius divided by the height is always 4 over 10. And now I can set up a relationship where I can figure out the radius in terms of the height, and this allows me to have a equation in terms of only one variable when I take the derivative. So the equation is given here, v is equal to 1/3 pi r squared h. I have to figure out whether I want things in terms of heights or radiuses, since this equation goes both ways. So I'm going to look back at the equation, and I want what is the rate of change of the water depth. That's a height. So I want everything in terms of heights when I take the derivative. So I actually do want to plug in 4/10 h for r. I should probably call this 2/5 h to save myself some math. Alright, v is equal to 1/3 pi times 2/5 h squared h. I should combine all these terms and everything before I take the derivative. 1/3 pi times 4/25 h cubed, and v is equal to 4 over 75 times pi h cubed. Okay, now I'm ready to take the derivative. I can pull the 3 down, and I get dv dt is equal to 12 over 75 times pi h squared dh dt. And I'm trying to solve for dh dt. So let's plug in all the stuff we know. We know, where are we? If water is being pumped into the tank at a rate of 2 cubic feet per minute, 2. What is the rate of change of the water depth in feet per minute when the depth is 5 feet? So we know h is 5. So 12 over 75 times pi times 25 dh dt. And something nice is going to happen. 25 divided by 75 is, this cancels out, and we can just get a 3 on the bottom. 12 divided by 3 is 4. So we just get 4 pi dh dt on this side. And then we just divide by 4 pi on both sides, and we get 1 over 2 pi. What are units? They are feet per minute. And that's what our dh dt is. So the height is increasing, and I almost made a mistake. So this dv dt, when I said it was 2, it's being pumped into. I didn't make a mistake. So you got to be very careful when you see these problems, whether or not the water is being pumped in or pumped out. In this particular problem, the water is being pumped in, so it's okay that our dh dt is increasing. But in a lot of these problems, water is leaking out, in which case you have to make this 2 a negative, and the height would be decreasing. So make sure you idiot check your answer and make sure it makes sense before you move on. And that's it.